Alrighty, in summary, we've got a few key points and a really big idea. The process of organizing data is how we extract value from it. So we're talking about big data, we're talking about data science, probably working with really large volumes of data, perhaps a lot of variety of data as well as volume. We want to organize the data to be able to get some sort of value out of it. To be able to organize data effectively, we can make use of a number of different types of technologies. Whether we've got graph data structures, we talked about representing real-world data as graphs. Whether we've got geometric data structures in terms of geospatial maps and things. Probabilistic data structures, and a number of different varieties of representation. And remember, when we talked about machine learning, one of the main things, one of the first points is represent your data so you can make it calculable. By leveraging the math specifically for those different types of ways of structuring the data, we can avoid problems that would otherwise come in by taking very ad hoc approaches. So let me try to break that down. If we've got a problem that involves a graph and we just want to go in and write some custom code to solve our graph queries, that's definitely doable, but it might be a big project. It makes a lot more sense to go and leverage some sort of open source graph query engine, use it right off the shelf. And what makes even more sense is to be able to leverage the math along with that to understand how to represent the problem to leverage the open source efficiently. That's really the gist of this workshop, is how can we combine both the necessary advanced math techniques with the kind of frameworks that you want to leverage for these big data problems. So all the time we're interested in making sure we've dotted the I's and crossed all the T's in terms of software engineering issues. How do we achieve less code volume? How do we try to get towards less latency, et cetera, less cost? So I want to go back to really the origins of the relational model. And if you've never looked at it, I definitely recommend. There's a paper down here, ACM paper by Edgar Codd, entitled A Relational Model of Data for Large Shared Data Banks. And this is, Edgar Codd's the person who came up with the relational model. So if you talk about relational databases, this is where it started. This paper here actually did the work back in 1969. An interesting thing is that he spent a long time trying to lobby to get any kind of vendors to adopt the relational model. And at the end of the day, IBM, after turning him down for a long time, actually came back around and launched a project having to do with SQL. And Edgar Codd spent the rest of his life talking about how bad SQL was. So if you really go back to the origins of the relational model, it had nothing to do with SQL. And that's a very important point to understand. Even so, rather than try to beleaguer the argument of SQL versus NoSQL, or structured versus unstructured data, let's really focus on what it is that apps do. Going all the way back to Edgar Codd, it's the process of organizing data. And this goes back to what we were talking about earlier in terms of graphs and matrices, sparse matrices, singular value decomposition, et cetera. We like to come up with these math formulations so we can get into very large scale data and adjust the knobs, adjust for the structure, turning the structure to be more general, or maybe turning it the other direction to be able to capture more variance. So we talked about that in the context of building recommender systems using SVDs. And that's really the big picture of what we're doing. We're adjusting the structure that's inherent within the data. Now, in terms of computational thinking, we'd like to propose a way of understanding how to approach big data, how to come up with apps. So number one, starting out with real-world data, it's usually pretty messy. Fortunately, though, most real-world data is probably going to be represented by a graph, or at least a lot of it is. So a good step is to start with the data that you've got and go out and use something like a graph query engine to test what kind of insights can you get from this? How is your representation doing? Are you actually getting towards the kind of solution that you need for a recommender or whatever you're trying to build? Once you've got your graph queries proving out conceptually, generally speaking, you can take a graph and convert it into a matrix, a sparse matrix. Once you've got that, then we've got great techniques and tools off the shelf, open source, for leveraging abstract algebra, functional programming, in the context of linear algebra to be able to go out and solve problems at scale. And the nice thing about this is it leads towards a lot of parallelism. So you can take that problem and move it off into a cluster and leverage Hadoop or Spark or whatever it is kind of framework you have, but be able to solve the problems in parallel at scale. And when you're doing that, mostly it's about optimization. Recall that, as in the last chapter here, when we talk about machine learning, it's really just a subset of optimization. A lot of the heavy lifting is, like I said, stochastic gradient descent. Things like quantum computers come along, maybe we'll knock that down exponentially in terms of the cost. And if so, then this whole rubric of how to go from real-world data to a cost-effective solution is what you want to keep in mind when you're approaching problems. In terms of computational thinking, there's an issue of pattern generalization and abstraction here. These different stages lead you from real-world data problems down to high return on investment apps, leveraging parallel processing, leveraging open source frameworks. The best apps out there will pull together these different areas, graph and matrix and functional programming, etc. But keep in mind that there's the need to adjust the structure within the data. That's why, at the end of the day, we're leveraging all this math, is how do we get those knobs and tune them? That's what we're doing in business when we take advantage of the math. In summary, a lot of this comes out of a very interdisciplinary effort. These teams are inherently interdisciplinary. We're building workflows. We're using these different techniques. Maybe quantum's good, but until then, we've got Minecraft at least. But this is our approach we're presenting for how to understand leveraging advanced math for these business use cases. I recommend a few follow-up recommended readings here. Data Science for Business by Foster Provost and Tom Fawcett. An O'Reilly book out last year, excellent, really goes into much more detail about applications of data science. Another great book, Doing Data Science, Straight Talk from the Front Line by Kathy O'Neill and Rachel Schutt. Also came out last year. And going more into like the data science aspects using Python, there's an excellent book by Wes McKinney, Python for Data Analysis. And with that, we have a long list of people we'd like to thank, more than we can actually mention, but I'll splash some names up here. A lot of people have really helped out in reviewing the material, both on the side of the mathematicians and the programming, as well as on the business side, and a lot of consultants and whatnot who have helped us. And please stay tuned for Just Enough Math. The book should be out this summer. Thank you very much.